All right, let's talk about periodicity. This particular topic has to do with something known as the effective nuclear charge. And simply put, the effective nuclear charge is the actual charge that the outer electrons, the valence electrons, get to see. Because the fact is that, yes, you do have a nucleus with some overall positive charge, but any of the electrons that reside farther in than the valence electrons actually get to see more of the charge of the nucleus. And the reason why is because every other electron, especially the ones that are closer to the nucleus, are going to be shielding away the charge of the nucleus. So instead of seeing maybe what is in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 18. So instead of saying an 18 plus charge, this particular electron may see at best 1.5, maybe a 2, but the rest of the charge is going to be shielded by the electrons that are closer to the nucleus, right? So they kind of like the picture depicts right here, they are shielding away that charge. And as a result, you have a different amount of energy attraction that's keeping this valence electron attached to the atom. And this changes from element to element, depending upon which orbitals are being occupied by the electrons. And so the effective nuclear charge changing allows for the atoms to have different properties, different sizes. Some of the properties can be physical or chemically in scope, but ultimately they come down to this idea of the effective nuclear charge. Now, when I actually go over the idea of periodicity in the next section, the next course in the chemistry series, I actually do introduce something known as Slater's rules, and I have my students calculate the value of the effective nuclear charge. But we are a little much too early for that. So in this class, I just want you to know and be aware of the effective nuclear charge being, in essence, the main reason why there is changes in chemical properties going from one element to another, even if the difference is only one proton. All right, so first let's take a look at the atomic radius of the elements. The elements, as they are arranged in the periodic table, if let's say take a look at the second row, if we look at the atomic radius, this is in angstroms, by the way. The atomic radius is depicted right here, 1.52 angstroms, 1.11, etc., etc. But as you scan this from left to right, generally speaking, what you find out is that the atomic radius tends to decrease as you go to the right of the periodic table. And you can see that to some degree also in fourth row, although there's some discrepancy happening here with the transition metals. There's a discrepancy that I address on the last portion of general chemistry. So for you guys, that will be 2 semester courses away from this course, right? So we won't be describing exactly why there's discrepancies here in the atomic radius of the transition metals. I just want you to notice that there are. But generally speaking, for the rest of the elements, there is that decrease in atomic radius going from left to right. At the same time, if you look at the groups and you see what happens as you go from top to bottom, almost without fail, all of the elements tend to increase as you go down the periodic table. And that's true for group 1, as it is for group 2, as it is for group 7, right? You see an increase in the atomic radius of the element. And generally speaking, this trend that going from left to right decreases the atomic radius of the element. This is attributed to the fact that going from left to right, the effective nuclear charge of the elements actually increases. And an increase in nuclear charge that's being felt by the valence electrons ultimately means that the electron is going to be contracted towards the nucleus, making the size of the element smaller. And when you go from top to bottom, the reason that you see an increase in the radius is because you are occupying higher and higher energy levels. And the larger the energy level value becomes, the bigger the radius of that element is in general, because you have to be farther and farther away to accommodate the extra electrons that are going to be present in that higher energy level. All right, so that's atomic radius. You have a decrease from left to right, an increase from top to bottom. Let's take a look at something known as ionization energy. First, let's define what that is. The ionization energy is the energy necessary to be put into the atom for such atom to lose its valence electron, at least one valence electron. So if you lose that valence electron, you're going to produce a species that will have a +1 charge. And on the other hand, if you acquire an electron, you'll produce a species that's negatively charged. But the idea is this: when you lose an electron, which is associated with the ionization energy, the size of the ion that you're going to produce is going to be smaller than the original atom that you form, and that's because you have produced now a positively charged species, making the electrons more attracted towards the nucleus. On the contrary, if you add an electron, you will create a negatively charged species, and because of the negative charge, now the electrons are going to be repelling each other more so they will actually expand and make an ion, an anion, that is larger than the neutral atom it derives from. Now, whereas losing an electron to form a positive cation is known as the ionization energy, gaining an electron to form the anion is known as the electron affinity. We're going to talk about those things in particular. But looking at the radii for ions, there's a table that I compile that shows you the periodic table, but within it, you have these values, 0.93, 0.78, 0.72, and then you have these superscripts. The superscripts actually tell you the charge the element can take up. In the case of vanadium, you could be 2 plus, 3 plus, 4 plus, 5 plus, and each one of those charges has an ionic radius associated with it. And notice that as the charge becomes more positive, the value of the radius becomes smaller. And the same thing is true for the negative charge. As the negative charge becomes more negative, the size of the element becomes larger. All right, now, generally speaking, but this is a little bit of comparing apples to oranges. If you scan the radii, the ionic radii going from left to right, generally speaking, you see a decrease in the ionic radius. But like I said, this is a little bit of an apples to orange comparison because the charges are not exactly equal. They're actually getting larger and larger, right? So it's not exactly a true comparison. Looking at the third row, same idea. The ionic radii sort of decrease in general going from left to right, but the charges are kind of changing a little bit. To some degree, you see somewhat the same trend of decrease for the transition metals, but there are discrepancies that you won't find out until you take the last semester series of general chemistry. I just want you to be aware of it by now, just in case you take a look at that and realize, wait a minute, something funky is going on there. There's a theory you'll learn in due time that will explain why this is happening, but that won't come until much later. So for now, we just want you to notice that there is a discrepancy for the transition metals. And it doesn't matter the charge. It could be 2 plus, 3 plus, 4 plus. The discrepancy is kind of shown throughout. But sticking out of the transition metals, if you see the trend from left to right, generally speaking, you see a decrease in that radius. And the place where it's super obvious is actually right here with the lanthanides, because all of them have the 3 plus charge, and I'm actually highlighting in bold the 3 plus charge ionic radius for each one of those species. And what you see when you look at the 3 plus charge for all of them is that indeed going from left to right, there is a very smooth decrease in the ionic radius of each one of these elements as you do go from left to right, while keeping the charge the same. Now that's an apples to apples comparison, so that's kind of what I'm going after here. So from left to right, you're going to see a decrease in the ionic radius because of the same reason that you saw a decrease in the atomic radius, namely that the effective nuclear charge is increasing from left to right. And from top to bottom, you see an increase in the ionic radius. And it doesn't matter which row you're looking at, or which column, you see the same general increase in radius going from top to bottom. All right, so yeah, general increase, increase, increase. So that increase in ionic radius going from top to bottom is attributed to the fact that you are, once again, populating energy levels that are of higher value and by default that are farther out in the atom. All right, so let's take a look now at this ionization energy and electron affinity. The ionization energy, once again, is associated with the energy that you need to put into the atom to remove its electron. And what you can see right here is that going from top to bottom, the ionization energy actually goes down. And that's true for group 1, it's true for group 7, it's true for group 2, and pretty much for the rest of the elements, that's going to be true. Go down the series, and generally speaking, you see an increase in the ionization energy, how much energy you need to put in to remove the electron. And the reason that could happen, and the reason it happens, is because a result of the fact that the electrons are farther away in the higher energy levels down in the periodic table means that their interaction with the nucleus is to a lesser extent. They get to see less charge, so they're farther away from the nucleus, but by default, because they're farther away and they do see less charge, they're easier to remove, so they take up less energy for you to ionize them. And when you look at the trend from left to right, you see that in general, there's an increase in the ionization energy. There's some discrepancies, although in the second row that we're going to address in a little bit. But generally speaking, from left to right, you see an increase in the ionization energy, and that's because the effective nuclear charge is going up. If the effective nuclear charge goes up, the interaction of attraction between the electron and the nucleus is larger, and now you have to put in more energy to break that extra positive interaction. So that's why the trends are happening the way they're happening for the ionization energy. And addressing the issues with the second row, this is actually kind of a trend that happens entirely with the group 3 and the group 6 elements. What you see is that going from left to right, there should be an increase in the ionization energy, and yet when you go from beryllium to boron, the value goes down. Then it starts increasing again, but by the time you get to nitrogen and you move on to oxygen, the value drops down once again, and then it starts going up. So why would it drop down when you get to boron and oxygen? The reason why has to do with the electron configurations of these elements. We compare beryllium to boron and we compare nitrogen to oxygen. The configuration for beryllium is 2s2, and the configuration for boron is 2s2, 2p1. The configuration for nitrogen is 2s2, 2p3, and that of oxygen is 2s2, 2p4. So when you draw out the electron configurations, what happens is that you realize that for beryllium, you have a full s orbital configuration. But for boron, the next electron has to actually be placed in a higher energy orbital, the 2p orbital. And because it's higher in energy than the 2s, automatically it takes less energy to remove than what you would have had to put in to remove the 2s electrons. For nitrogen, it's a similar story. You have filled up the 2s electrons, but then you have the 2p orbitals partly filled up. By the time you get to oxygen, not only are the 3 boxes filled in with 1 electron, but now you have a fourth one that is present in the first box. And because you have now placed an electron in a box that already had an electron, you encounter electron-electron repulsion that makes it less likely for this electron to be as happy to be in this box as the other 2 are, which don't have an extra electron present there. So as a result of that, the energy drops down because you have a little bit of a repulsive interaction going on between those 2 electrons. All right, so this kind of explains some of the discrepancies we're seeing. All right, now we're almost at the end. Let's talk about the metallic character. Now this is a little bit silly, but pretty much the metallic character, as you might expect, has to do with where you are in the periodic table and how close to the metals are you. And if you look carefully, you realize that yes, the vast majority of the table is composed of metals, but specifically the metals are to the left of the diagonal here, right to the left. And for sure, if you go down, you're going to find metals. Otherwise, if you move to the right of the diagonal, you have non-metals, and the farther up you go, the more likely it is for you to find non-metals. So, simply stated, for you to find metals or for you to look at the metallic character, an element is going to be more metallic if you move further to the left and you move further down. And one way to look at it is that the metallic character is increasing going to the left because the ionization energy decreases. Okay, so to be a metal, in other words, is to lose electrons more easily. And you will be able to lose electrons more easily if your ionization energy is lower. So with that idea in mind, another way to decrease the ionization energy is to go from top to bottom. And if you go from top to bottom, then you expect to have greater metallic character because once again, the ionization energy will decrease going down and towards the left in the periodic table. All right, the last thing is electronegativity. The electronegativity is an idea regarding how good, how well each atom is at attracting electrons towards itself. And when you start combining elements of different kinds to each other, the thing is that one atom will be better at attracting electrons than the other. So the mere fact of making a bond between them will develop a partial negative charge on one of them and a partial positive charge on the other one, with the one with the partial negative charge being the one that attracts electrons more easily towards itself. And the tendency of this ability to attract electrons is what we call the electronegativity. So, and also we depict that attraction with a dipole arrow pointing towards the more electronegative atom. All right, so looking at the periodic table, this time around showing you the actual values of electronegativity here, what you're going to see is that typically you have values ranging from about 0.5 all the way to almost 4. And that's really the range for electronegativity. So fluorine, as you can see in the table, is the most electronegative atom. And on the other hand, francium is the least electronegative atom, right? And moreover, if you look at the trend from top to bottom, you see that decrease in electronegativity in pretty much all the elements. And the reason that electronegativity is decreasing, right, the ability to attract electrons towards itself is decreasing is because the ionization energy is going down. And the reason it's going down is because the atomic radius is increasing, right? So you have less of a tendency to attract electrons as a result of all these related properties. And going from left to right, what you're going to find out is that the electronegativity tends to increase. And that's because the effective nuclear charge is increasing. So to kind of summarize all of this, when looking at the table, this is basically one way to kind of look at the entire thing. Going from right to left or going from top to bottom, the atomic radius, the ionic radius, the metallic character are all going to increase. By going from right to left or top to bottom, the ionization energy and the electronegativity will decrease. So if you look at it from this point of view, the whole set of explanations actually boil down to basically one sentence, which is kind of funny considering that this video is already kind of like around 18 minutes long. But generally speaking, the way this is going to be tested on exams and homeworks is that I'll give you a set of elements. It could be like phosphorus, sulfur, arsenic, and selenium, and I can ask you, arrange them in order of increasing electronegativity or metallic character, etc., etc. And you just have to follow the trends in the periodicity of the elements based on this table. All right. With all that being said, this is the end of lecture 8. So I'll see you on the next set of videos in the next lecture.